So in this example, we want to find the mass of the solid bounded by x equals 0, y equals 0, z equals 0, so the coordinate planes, y equals e to the negative z, x equals 2, z equals 1. What a mess. All right, given the density function delta equals x plus 1 with units in grams per cubic centimeters. Okay, so let's see here. We need to figure out what this looks like. So I went and graphed it in Maple. You don't graph the density. Density is just, how much stuff is in the object at various points in its mass or in its volume. So you don't really worry about that, but you want to look at it for what it looks like. Okay, so I have z equals 1, right? And then I have z equals 0 down at the bottom because it says it's bounded by the coordinate planes. And then I have z equals the negative natural log of y. Because if I'm doing plot 3D, it's always z equals. So the function was given to me in the form y equals e to the negative z right here. But that's not useful to me for plotting in plot 3D. So I switched it around. I took the log of both sides. And that got me the negative natural log of y. So z equals the negative natural log of y, which is that rainbow surface right there. So there we have it. So we're graphing this piece and we're trying to find the volume, or excuse me, the mass of it. So it has some density. There's some, amount of stuff inside of it at various spots, but that's beyond our purview and not on our ability to draw in Maple anyway. The best you could do is orient the colors that you're drawing with somehow, but that's not going to happen. Okay, so let's go draw this on our paper, or at least try to. So it's a little bit like a skateboard ramp, if you've ever seen a skateboard ramp. So you have your surface like this, and then you have z equals 1 is right here, and then it's coming out and curving down, and then it touches out here. Like that. Okay, that's not bad. All right, so this is the x-axis, this is the y-axis, this is the z-axis. Okay, so we have to think about which way we want to orient ourselves for our region of integration. And the easiest way to do this one would be to do, okay, so if we went with the xy plane, the problem is that through some of it, it's a curved surface, and through some of it, it's this flat surface. You can kind of see it better in Maple. So you don't want to orient with the xy plane, even though I drew that down there, but I just drew it down there so you could see it. So that's not going to be any good for us, because we would do one triple integral for this section, which has the rainbow top, and then another triple integral for this section, which has the red top. Nah, that's no good. Okay, so then which way do we want to go then? Do we want to go straight back to that white wall? And the answer is, it'd probably be okay, but it's not great because it has this curved surface. So that wouldn't be so fun. The easiest way is actually to barrel through and drill backwards and have it be the XZ plane that's our region of integration. So that's what we're going to do. So it's not a question of can you do it the other ways? You probably could, but the other ways are more difficult. So it's easiest to go this way because that's our rectangle. And rectangles are easier to work with than this, whatever this is, right? And it's definitely easier than going from the XY plane because the XY plane will be really tough. You'll have to do two different sets of triple integrals, and nobody wants that, right? So we're going to do XZ plane. So let's redraw our region of integration. So this is the surface right here. Oop, I can spell surface. And then the region is really easy, right? We just have to kind of figure it out. But we know that it's a straight line, right? And a straight line. It is a rectangle. So all we have to do is figure out our values. Oh, wait, except they were given. It tells us that z equals 1 and x equals 2. So there you have it, folks. Right? That's a very easy region of integration. Right? It's an easy region of integration, and when you put the pillars in, they're only going to hit, which I'm terrible at drawing these pillars, I'm sorry. But when you put those pillars in, they're going to go backwards to that region of integration and outwards and hitting this curved surface right here, right? So that curved surface right? That's y equals e to the negative z, right? But then this back wall is y equals 0. So that's not going to be that difficult, right? Okay, so let's write our triple integral. So the mass is equal to the triple integral over the solid of the density function dv. My density function looks a little funky. Hold on. Density. There we go. That's delta. Okay, so this is going to be the triple integral. Density was given to us. It's x plus 1. So x plus 1. And then the way we are orienting this is definitely dy first. Right? So I'm going to do dy. Then I have my choice. I mean, it doesn't make any difference down here, but I'm going to go vertical because, again, if you don't have if it doesn't matter, then why not vertical? It's more comfortable for us. So that would be dz dx. So I'm going to do dz next, and then I'll do dx next. Okay, well, x is 0 to 2. Z is 0 to 1. So far, this is not hard. Right? This is not difficult. All right, what about y? Well, we start at the back with our pillars. So the pillars would be stacking in here to find the volume. 0 would be the bottom. And then this surface, e to the negative z, would be the top. Done. So it really paid for us to do y first because we already had our function solved for y right here. So that really made sense to go this way, right, and have the xz plane. All right. Sorry, that is really bugging me. So that's the pillar. Okay, so let's just integrate this. Now, unfortunately, we can't use our trick. So you can't get rid of z because there's a z right there in that integrand. And you can't get rid of x because x is right there. So we cannot use the trick. So we'll make a little note. Right, we're going to have to do this whole integral. Note, right, x and z are present, so we cannot use the trick. Right, we're just going to have to integrate. All right, well, luckily this isn't too terrible. All right, so the integral of x plus 1 with respect to y would just be x plus 1 times y. So we're going to say the integral from 0 to 2, then the integral from 0 to 1, and then this is going to be x plus 1 times y, and y is going to go from 0 to e to the negative z, dz dx. All right, so we just put in e to the negative z. So this is the integral from 0 to 2, and then the integral from 0 to 1. And then that will, of course, be x plus 1 e to the z, or e to the negative z, sorry. Then dz dx. Okay. Well, the integral of e to the negative z is just negative e to the negative z. So that's not hard. So this is the integral from 0 to 2, and then x plus 1. And this would be times negative e to the negative z. And then we're taking this from z equals 0 to z equals 1 dx. And again, I'm just putting the z ins there just to help myself, just to remind myself of what I'm doing. Like these were y values right here. These are z values. Okay, so then now this is a transcendental function. You actually have to put these values in. A lot of students get too used to e to the 0 being, well, when they substitute the 0 in, it's nothing. But this 0 going in is going to make something. So you got to be careful. Okay, so this is the integral from 0 to 2. And then this is x plus 1 times negative e to the negative 1 minus negative e to the 0 dx. Okay, well, e to the 0 is 1, right? So that's 1. And then a negative power is really 1 over, right? So this is 1 plus 1 over e, if you will. So this is the integral from 0 to 2 of x plus 1 times, okay, negative 1 would be 1 minus 1 over e dx. And of course we're going to make Maple do this. Like, we're not going to bother. Although that whole thing became a constant anyway, so it doesn't really make any difference. You could pull it out entirely. But and the integral of this would be 1/2 x squared plus x. And then you would just have to stick 2 into it. But that's okay. We can make Maple do it. All right, so here's my original integral. X plus 1, y equals 0 to e to the negative z, and so on and so forth. And I got that as 4 minus 4 e to the negative 1, which is 2.528. And then, oops, I just realized a mistake there. But I realized I wanted it to be numeric so that I had it defined numerically. And then I did my last integral that we just found. And sure enough, it's the same thing. 4 minus 4 over e is also 2.528. So this comes out to 4 minus 4 over e, or 2.528. Okay, now we're finding mass. Mass is grams, right? Grams per volume. Volume is cubic centimeters. So this mass would be in grams. Because grams is a measurement of mass.